we can start.
So good afternoon, everyone. Can you hear me well?
Yes.
Okay. How about from that corner? Can you hear me well? Good. Okay. So welcome everyone to VinUni seminars. And today we have Professor Hadi Law from Singapore Management Universities. So Professor Hadi is a program director of the Bachelor of Science in Computer Science program at SMU. And he's also leading a research group called Preferred.AI, which focus on apparently preference analytics and recommendations. And just so you know, he's one of my PhD advisors. So if you have questions about computer science, data science, or PhD research in general, you can ask him after the seminars, right? So we have a lot of students and also PhD students, and I think current PhD student as well. So feel free to ask him about the way that you can do research as well as orienting in choosing topics, if you will. Okay. So without further ado, I would like to invite Professor Hadi to present and share his research and actually the group research on learning, representing, and interpreting multifaceted preferences for recommendations. So let's welcome him, and please.
All right, so good afternoon, everyone. So thanks for the introduction. All right, so this is my first time to VinUni. So far, I think I'm very impressed by YRC. And one of the things that I would like to do today is also to get to know you. So I hope that by sharing some of the things that we do, I think you get a sense of where we are coming from, and feel free to share your perspectives as well. So I come from Singapore Management University. So we have a School of Computer Information Systems. So that's where I come from. That's basically what I do, which is I've been focusing on the idea of modeling preferences for recommendations. This is something that I've been pursuing for the last 10 years. So I think part of the talk, I also want to share some of the evolution in the way that we thought about this problem over time, and what are some of the latest thinking about some of these issues. So this is the Preferred.AI group, right? So if you see someone familiar, right? But he looks a bit younger. Okay, so this was actually taken a few years ago. Some of the people are still around, some of them have graduated. And of course, in a university, the nice thing is that people come, they grow, and then they go, right? So that's also what we hope, that most of you are going to grow in your time here and eventually go on to greater things as well. Now, this is kind of like an overview of our research. I think if you kind of think about ideas of recommendations, and a lot of the information that we consider come from reviews. So in the early days, especially in terms of the e-commerce space, people are, it was still based on the web as opposed to the app. And when people are on the web, they are much more participatory in the sense of like writing text reviews and so on. So those become a major part of what we study as well, right? So now, if I go to ChatGPT and kind of ask them to kind of summarize what we do, there are a few different things. But some of the most important things are essential recommendation systems and preference learning. And I think here I want to spend a bit of time to talk about why is it that the issue of preferences is so interesting. So if you think about the evolution of the web, at the beginning we used the internet to almost like a library. So meaning that it's the place where you store information. So in the early days, you just store web pages, right? In fact, I think one of the killer apps of the internet is Wikipedia. So that's where you store a lot of objective information about the world. And in fact, the way that we think about large language models today, like ChatGPT and so on, we still think of it as almost like a source of information about the world. Now, while that is one thing that we can use the internet for, increasingly, what we realize is that what people most find interesting are each other. Meaning that we are most interested in people, we're most interested in society and what we do together. And I think that's where I think this issue of subjective information, meaning knowing not just about what the world is, but importantly, who are the people in it, and why they do what they do, and what sort of preferences drive them to do things in a different way. I think increasingly that is the more important aspect. I mean, until today, if you ask ChatGPT what your mother wants for a birthday, right, they might be able to give you an answer given like based on what mothers generally like, right? But let's say your own mother, then in that sense, I think there's a lot more personal information that is involved. So I think that has kept us interested in the problem for a while. And in that sense, I think the way that we thought about the problem, I just want to share with you the way that we thought about the problem. And it seems to us to be almost completing on a full circle. So in the early days, I think it was kicked off a lot of it by the Netflix Data Challenge. That was, I think, almost 20 years ago now. Where they held this competition where people can do rating prediction for movies, and you get $1 million. Okay, so $1 million is not as much as the FinFuture prize, right? But 20 years ago, $1 million is still a good money, and yet it was still a very difficult problem. And a big part of the thinking was that you watch people by what they do, so not what they say. So you look at the movies that they watch, you look at how they rate, and in that way you learn a bit more about the sort of preferences that they have. So then a big part of machine learning that goes into it really thinks about how do we solve this prediction problem of what people are going to adopt or rate and so on. And in some sense, it is some of the most difficult problem, because if you do a lot of like data science, classification, and those kind of problems, generally you have some testing data, training data, and validation data, right? But the way we generally pursue these problems is that what we consider to be the test data is usually a lot smaller. So I think if you've done some data science project in the past, so then you have to split it, training, testing, and validation, right? So most of the time, your training data is the largest part of it. So you can say, all right, I'm gonna take 60 to 80% to be the training data, then maybe some 10, 20% to validation, and the remaining for the test. Now, the interesting thing is that for a lot of these kind of problems, where we are trying to predict ratings or adoptions, you basically have a matrix of users and items, and the way that the users are going to rate different items. Now, most of these are very sparse, that in the sense that for a lot of the real world data sets that we see, the sparsity is like 99%. Meaning your matrix, out of the 100%, 99% is missing. So that means that you are trying to train with the 1%, but you're trying to predict the 99%. So, and that remains still a very difficult problem. I think, in fact, if you kind of go to a lot of the literature, research literature, some of the performance numbers of the research algorithms, at least validated on some benchmark data sets, they are still in a very low digits in that sense, because the problem is indeed very hard. Now, over time, at least the thinking is that, well, if this problem is primarily driven by sparsity, and where does the sparsity come from? They come from the lack of information about what users actually do. And part of it is because we don't always do ratings, right? Because ratings is only one part of it. The other part of it is, we don't have a chance to interact with every single product we might like in the future. So in that sense, I think there is a big sparsity. So then the question then is, how do we inject something that is going to help us to address this sparse information? And that the answer to that, at least the way that our group was thinking about this, is to make use of additional data. And this data usually comes in the form of information about the items, the users, and the products, right? Now, what sort of information do they come in from? They come from reviews, they come from product images, and so in a way, if you think about the problem recommendation, essentially I sometimes think of it as a problem of similarity or matching. You're just trying to connect users to the items that they might like, and so that connections might cross over different spaces, So that could mean that you look at the kind of products that they have adopted in the past, you look at the text reviews that they have written, and trying to understand how the users actually explain the way that they like things, or you look at the images, because for example, a lot of us have a certain kind of a visual way of looking at things, right? So if you're shopping for clothes, for example, you're gonna be looking at certain kind of clothing and so on. So a big part of it is really in terms of how do we improve the accuracy by injecting information from text, images, as well as graph. Now, it does boost the performance by quite a lot, right? In fact, we spent a bit of time to really try to look at how do we improve the performance of these things. And one of the things that we did is this idea of Cognac, which is a Python-based library. So if you're going to do data science projects and if you want to do recommendation problems, come and visit Cognac. So it's a free framework for you to essentially look at some of the recommendation algorithms. Now, it has a lot of algorithms, and importantly, it does a couple of things that I think are very nice. One is this idea that it can absorb different kind of modalities. So there are recommendation algorithms that have been designed for text, images, and graphs. So we kind of build them into the library. But one of the observations that we had is that a lot of times, this essentially becomes just a representation of the data. You might design an algorithm for text-based recommendation, but at the end of the day, the text becomes some form of representation vectors. And if you deal with images, you will still end up with some form of representational vectors, which means that there is a steady degree of interoperability between different recommendation algorithms. So a text-based algorithms, you can still use it for image data. An image-based algorithms, you can still use it for text data. And some of these things are essentially built into Cognitive. Now, the second thing, which I think is very nice, is this idea of experimentation. So a big part of research is trying to do things in a repeatable, reproducible way. And so we try to put it as a framework that makes it easy for you to compare different recommendation algorithms across like same benchmark, same way of data split, so that when you get the results, it's actually really repeatable. So in fact, I think this is part of the reason why Cognac is actually included as one of the recommended libraries for experimentation by the Recommended Systems Conference in 2023. Now, but this is not kind of what I want to talk about today, right? Because I'm going to talk a little bit about the last piece of it, and this is some of the later part of our thinking, which is that, well, although initially we thought of the modality, what we call the additional data set, text, images, and so on, as a source of information to improve accuracy because it addresses sparsity. It turns out that there's another value to having these additional modalities. And the reason is because some of this information about human behavior are actually very difficult to interpret. If you just watch someone in a shop, right, for example, and if the only thing you can do is just observe the person walking around in the shop, just looking at things, picking things up and so on, it's not very easy to understand or to interpret what it is that he or she is looking for or what sort of preferences he or she has. Now, but in the web, we realize that things that are online, they get documented much better, because when you click on something, I can take a look at what is the text description of that thing that you just look at, what does it look like in terms of the images and so on. And that helps us to derive a certain kind of profile to try to understand your preferences better. So meaning that at the end of the day, the true value of having additional modality in terms of these text, images, and graph and so on, they are not just there to improve accuracy, but they provide us humans a different way of understanding the user preferences. And I think this is kind of where we have been focusing on in the last few years, in terms of how do we look at recommendation problems and how do we get to a point where things become a bit more explainable, things become a little bit more interpretable. And so I'm just going to describe to you like a few pieces of work in this direction. and some of the reasoning that goes into why we do things in a certain way. Right? So the first thing is to look at explanations. And I think here is this idea that, well, we think that the way that we frame recommendation problems is that I ask you, I try to predict what you're going to buy in the future. And then I'm going to see whether or not my prediction is correct. But that is assuming a world in which the recommendation itself doesn't influence your action. But we all know that if you go to a shop, right, the salesperson actually does matter in whether or not you're going to buy an item. Because in a way, the way that the recommendation is presented to you in itself is going to be influential in whether or not you're going to eventually purchase the item. So meaning that there is going to be a layer that comes after the recommendation algorithm, but in terms of how is it presented to the user, that actually matters. Now, there are many pieces of work that try to look at this in different ways. For example, if you're looking at clothing, it might be that I need to show you the kind of clothes, like a certain kind of a image that you might look, or I might pinpoint to you which part of the clothing is this that you like. Maybe it has a special pattern in some ways, right? But in this work, we are looking at the idea of trying to improve explanations. Now, this was done some time back. I think it was a few years ago. In a way, I think even before the LLMs went big and so on, we are looking at where cases where even the generative abilities of the machine learning models are still very limited. And in that sense, a lot of the recommendation explanations that you might see, in fact, you still see them today, is that it becomes almost like a template. So you might go to some website and then they're trying to recommend you some item, and they'll say that, oh, you might like this, you might like that. Why? Then they give you some boilerplate information, like okay, it's something that performs well, it's something that performs badly, and in that way, I think you don't get a lot of information of what you do. Now, this is one of the things that that I like about this work is this thinking that although we look at problems in terms of learning problems, but there is a way to understand problems, not just in terms of learning, but in terms of the computational complexity of the problems. And I think in this particular work, the way that we approached the problem was that, hey, maybe instead of generating an explanation, because generation, it becomes repetitive and deterministic, maybe we can have a way to synthesize an explanation. And the difference between generation and synthesis is that in generating, you're trying to completely do things from scratch. In synthesis, what you try to do then is to try to look at different pieces of text from places, and then you try to recombine them to make a new piece of text. And here the insight is that if you look at the reviews of a particular product, and products now have a lot of reviews. So if you go to these different e-commerce sites, there are many reviews. I understand that app-based reviews now have very short reviews, right? Sometimes they don't even talk about the product, they talk about the shipping and so on. But if you go to the web-based reviews are usually a lot more lengthy and extensive. I think partly because people do things on computer where they can type as opposed to phones where we just use their thumb to write very short reviews. But because there are many sentences that come from various reviews, you can recombine them. You pick some sentence from this review, pick another sentence from a different review, but in so doing, you may then piece together a new explanation. And that's kind of what we try to do. So now there are two parts to this. One is, can we construct an explanation? And then there is a personalization aspect to it where you need to personalize it to the person that you're presenting it to. Because I might build a certain template based on the sentences that I get from the reviews, but then I need to customize it to you by looking at some of the sentiments that you might have for different aspects. So I'm just going to give you an example of some of these things, right? So this is what you get from a template. Like, you might be interested in the following aspects of tripod, construction, price. This is basically cameras. And this is what you get by doing synthesis. And these are sentences that are extracted from different reviews. So then there are different considerations. I think one of them is whether or not it contains the different aspects and whether they cover representative aspects that you get. Now, if you go to Amazon today, they do something similar, but they do it in a generative way. So they do a summary. Now, in the summarization, basically they try to look at the reviews and then try to find a summary. People say this and that and so on. But here there is a customizable part where the selection of the different aspects that become part of this explanation, as well as some of the what we call the opinion phrases, like whether it's solid, reasonable, and so on. These are going to be customized to the end users at hand. And I think that's something that, at least for now, Amazon is not doing it yet. They are not yet personalizing the explanations to the users. This is basically just another set of baselines and so on, right? So now this is one way in which we are looking at a problem. How do we present a better explanation to the end users? Now, so on the other hand, when we do actually work with Amazon, so one of the students actually interned with Amazon, and he was being asked to look at a problem. One of the things that we realized is that this notion of personalized data, meaning what you buy, what you do, what you like, what you dislike, and so on, these are data that are very difficult to get hold on, in the sense that Amazon is not really willing to share a lot of this data with us. So essentially then the problem becomes, how do we work on something meaningful while still making something that is useful? And it turns out that there is a problem that Amazon present to us, and the problem is the following. They can come up with a recommendation, but a lot of times they can't really present it to the user in a way that is actually customized to the users, right? So for example, let's say, okay, let me find an example. Okay, so I didn't have that example here, but let's say this is an example of a product title. Now, this is, if you look at a product title, you probably get a sense of what it is. It's a dress, like a piece of clothing, right? But the way that the seller is going to feature the product, it's not very easy to understand, because they're gonna put every keyword there. And because the anticipation is that if they put every keyword there, eventually one of the keywords is gonna be the keyword that you use to search for the product. So in a sense that it is an interface that is optimized not for you to understand what the product is, but it's an interface that is optimized for you to find their product, or for their product to eventually surface higher to you. So now, in the case that we are looking at recommendations that are part of Reels. So meaning you will go to a website, right? And then you will say, okay, I'm looking for a TV, and then it will show you a list of TVs. Now, when you look at the list of things like this, part of the problem is understanding why are they even comparable. So meaning that it is not a problem of just coming up with individual independent recommendations, but really how do you understand things at a level that allows you to compare different things. Because if you think about what an act of shopping is basically a decision making act. You're trying to understand the choices that you actually have, so that you can then make a decision. So now, in order to improve this explanatory capability, so then we had to do two things. So one is, ironically, is that we need to simplify the product titles. But we need to simplify it in a way that makes it comparable. So meaning that if you then look at these two different product titles, and sum was the proposed algorithm. So you look at the two product titles at the end, right? So they get simplified into something that is a little bit more comparable. So first of all, they're going to have a short description, and then we're going to point out certain aspects that are most important to certain categories. So in this case, for example, like a material, right? It's whether it's a chiffon or leather. What is the color? What is the size? Because it turns out that you buy fashion items, these are the three things that you are looking at. What is the material? What is the color? What is the size? Now, in so doing, then it becomes more comparable. So that allows us to do things like this, where if you are presented with TVs, right, or other products and so on, the way that the product titles are going to be customized, they're going to be customized to make it more comparable to one another. So in this case, you can see that they're all TVs, right? So there is a certain degree of what is the brand, what is the size, what is the resolution, and then there is like which year model they're gonna come from. So then if your intent is to try to make comparisons, you can actually do that very easily.
So,
Right? Yes.
quick question. So, the use case is make it easier for the buyer to make comparisons.
The use case is to, yes, so basically the use case is that if you go to a product on Amazon,
Yeah.
then they have reels.
Yeah.
So usually they will say more products to consider,
Yeah.
or similar products to these other products.
Yeah.
But a lot of times the consumers are telling us that they don't understand how are they similar, how are they, why should they be considering these products. So then the intent is to make these recommendations surface in a way, because when you're looking at a product page, you're trying to understand how is it relevant, like all these recommendations that you're seeing, how is it relevant to this one.
I see. Because I thought like, because you have the issue like the merchant who upload their product and they try to put a lot of text.
So they are effectively abusing the system.
Yeah, abusing it, and then you try to make it more concise, but still keeping the important information, so that the product is still searchable by the search engine.
But in this case, because the products are not, it's not to improve the searchability,
right,
but to improve the presentation. So essentially the thinking is that the way that you search for a product and the way that you are comparing the products don't have to be the same. Right. So the product can have multiple representation, some representation to be in the search index, another representation for display.
I see. Okay.
So that's the use case. And the second thing is to come up with these titles, which is what should be the title that accompany the recommendations, which in this case is more TVs, OLED technology, different display sizes. Essentially is emphasizing what is in common and what is different. Now, coming to how it's done, basically the overall methodology is a two-level summarization. You have to look at the different product titles and summarize them. But there's going to be a dependency in the way that the products are summarized, because you're trying to summarize not one product at a time, where you're trying to summarize a sequence of products as part of the recommendation, and you want them to have comparable titles. And then once you've got a new summary, then after that you can accumulate all these different products and come up with a summary for the category title. So in that case, then if you receive a recommendation, then at least you get a little bit more interpretation in terms of what it is that the user is looking at. All right.
Are they putting this in production?
They are putting this in production for some categories. And then they call it soft lines. Soft lines are less structured products, like
yeah. Just like a very not like hard categorization, but
yes.
They generate on the fly.
Right. Yeah. Okay. Now I'm going to touch on another piece of work, but in this way, I think I want to introduce some other concepts that we kind of look at as well. But basically, if you look at the past couple of things, I mean, what we are trying to do is that we are trying to improve explainability. Explainability in the sense that if you present recommendations to the users, how can we explain it to the user? So that means that the intended recipient of the explanation is the receiver of the recommendation, right? But as we look into these sort of problems, we start to realize that there are actually two types of explanations that you want. There is the kind of explanations that you want to give to the end user because they try to make sense of why this is being recommended to them. But on the other hand, there is also the explanation that you need to give to yourself as the person who designed these algorithms to try to understand the workings of the model. Now, for lack of a better term, we're going to use the term interpretability for this second term, for this second aspect of it. So explainability is how I explain it to the customer. interpretable is how do I, as the designer of the model or as someone who is running the algorithms, try to interpret the outcomes of these things. And it turns out that all these things, while it might seem useful to the end user, but they are, in a way, they are not directly explanatory of the underlying algorithms that are actually driving the performance of these predictions. So that's where we start to look into problems that we basically look at the idea of disentanglement. And I think I'm going to explain a little bit what is this concept of disentanglement. The thinking here is the following. So if you think about a lot of what recommendation algorithms do, like what we call like matrix factorization and so on, they are at a very high level is some form of clustering. So basically I need to cluster the users into similar type of users. I need to cluster the items or the products into similar types of products. And this is actually something that I thought is very interesting, right? Because very early on, when I started thinking about personalization, I thought of personalization is about a problem of how do we know what makes a person unique. But over time, I realized that if it is true that personalization is something that makes a person unique, then it's not something that we can learn from data. And the reason is because we don't have enough data. So that means that the only way we can build a model for personalization is not by understanding how a person is unique, but instead by understanding who are the other people who are similar to this user. So meaning, to personalize things to you, I actually need to find out who else are similar to you. And I think that is a big driver of the way we think about this sort of a methodology. Now, a lot of times, what it means is that we have to form some kind of vectors. What we call, you probably are familiar with the notion of vectors, basically like some sort of feature representations, right? So these features, you can think of them as almost of an alignment or an assignment or affiliation to a particular cluster. So if you have if you're strong on one factor but on other factors, means that you belong to a particular cluster. Maybe some users are into horror movies. So in that case, you're going to cluster people who like horror movies as well as the horror movies themselves, right? Or some other ones, they like a romantic comedy. It's probably a different cluster of users and a different cluster of items and so on. Now, but because these different things are not always easily separable, it turns out that when we build clusters, we tend to get confused easily. So for example, right, let's say, if I take a room like this, and let's say I try to understand who are the people in the room, I can start to do some clustering. But the clusters, a lot of you are probably having something similar. Some of you come from this program, some of you come from that program, some come from this research group, some come from a different research group, or you're sitting in different places. So in that sense, there is a lot of different ways and I can do clustering. And yet, all those clusters might actually be just relying on a few dominant features. So meaning that the idea of disentanglement is this key thinking that if I want to learn multiple factors, I want them to be as independent as possible. In fact, I think you might have learned this very similar concept if you have learned PCA, right? Yeah, I see some. Do you learn PCA, Principal Component Analysis? I guess they learn it, right? Yeah. Yeah. So these are some very basic statistical tool. But the thinking is that you try to reduce your data dimensions to the extent that your dimensions should be as orthogonal or as independent from one another as possible. And the reason is because if you find decorrelated dimensions, then you can do a better compression. And then it also allows you to kind of do what you call a compositionality. You can combine some of the factors together. Now, so the idea of disentanglement is to focus on the factors that you learn, and then asking the question of how do we make all these factors as different from one another as possible. Because in that case, then we make the best use of the number of parameter space that we have, Because if I can make the model learn this particular aspect well, then in that case, then I don't have to waste some of the other factors, because then I can use the remaining factors to basically focus on things that are different. So that is the idea behind this entanglement, and I'm just going to show you. This is a way of doing this through variational autoencoders. I think at the beginning of the talk I saw some people talking about autoencoders, right? So, okay, I'm not going to belabor the point, right? Because that's not really what I want to focus on. But the basic idea here is that instead of relying on a single autoencoder, the idea here is to first try to get a sense of how the data itself, what is the clustering structure. So in that sense, we look at this is a user vector in terms of which items they have interacted with in the past. And then we might try to cluster the items in a sub-clustering way. And then we're going to build an autoencoder such that we're going to focus on one cluster at a time. All right, so then in that case, then we are going to get what we call this entangled representation, because they are different factors, and these factors basically are focusing on different substates of the data.
But what's the clustering algorithms?
Basically some form of k-means, but in a soft way.
But then you need to have like embedding vectors, right, of those factors.
Yeah, so this is a part of the model itself. That means like you have to learn embedding vectors as well.
But you need to define the number of clusters.
Yes, you need to number of clusters, yeah. So that's something we never get away from clustering. You need to define the number of clusters, yeah. So this is Preferred.AI. It's not our word, but we use it a lot as a base model in terms of how we... so the thinking here is now is that how do we understand these factors? Because at the end of the day, you get clusters, but how do we really understand what these clusters actually mean? And I'm just going to quickly describe two different ways that we look into this problem. One way is to look at the text. The other one is to look at the compositionality of the problem. Now, in the text way, the thinking here is that let's not just do with one, because this is how we use the multimodality idea. We don't deal with just one disentanglement. We're going to create a second one, and it's going to be based on the user texts. User texts come from the reviews that they have written, or maybe some self-descriptions and so on. But then you get a representation of the user in the textual space. You get a representation of the user in the rating space. And then by aligning these factors, aligning means that you try to find out which part here is connected to which part here. Then you get a one-to-one, right, in a soft way, but you get an alignment that will then tell you some degree of which factor in the text is most connected to which factor in the preference space. Now, the preference space are just numbers, but the text can be transposed into the words, and at least for us, we understand the words. So meaning that then, after we align, let's say, the first factor and this factor, then we can then interpret this factor in the textual space. Basically, we almost trying to do a translation from the preference space to the text space. Okay, this is a very complicated thing, okay, so don't worry about it, right? So I'm just going to focus on some of the way in which this is applied. So we applied this on citation data, so meaning that which papers cite which other papers and so on. So in that sense, I can look at the papers that you co-authored, so then I look at the abstracts, that becomes a user text representation. And then by looking into the things that you cite, right, so it's the papers that you cite, we can then break down a recommendation problem, but then here are going to be so-called the factor words. So this is what you basically get out of the second one. But this is going to be tied together to each of the user space. So then in the end, what you're going to get is some degree of interpretability, because then I can take a look at the different factors that the user has, and then I can have some degree of interpretability in terms of the words that are most connected to those latent factors that derive a recommendation. So essentially, we are trying to superimpose the words onto the preference space. Now, this is one way in which we can try to do the interpretation. The second way is by looking at the concept of compositionality. Now, here is another example. So suppose that we are looking at shoes in particular, right? And you can have different attributes, like the shoes may have different brand. So is it Adidas or is it Nike, for example, right? Or you can have different color. Is it white? Is it green? Is it pink? Or you can have you can look at the cuff, right? Some are high cuff, the other one is low cuff, right? So it means like you have two different types of shoes, right? Now, if you try to describe every possible one of them, then you're gonna have 2 times 3 times 2. Then in the combinatorial space, you have 12 different possible combinations. And so then the 12 possible different combinations are gonna give you, let's say, the clustering at the top. Now, but there are 2 problems with this, right? The first problem is that we can't possibly produce all the possible combinations because some of the data that we have actually have a high number of attributes. And the second problem with this is that in reality, in the real world, you don't get all these things at the same frequency. So meaning when you try to discover these clusters automatically from data, you won't discover all or most of them because they're going to be hidden by the more popular clusters, like the bigger ones. So then the bigger ones tend to dominate the output of the clustering. So the thinking then is that, well, if you know for a fact how all these different things, right? Let's say what is the brand, what is the color, what is the height, then you can actually split them into multiple facets. Now, you don't have to know, right? In the algorithm, we don't assume that we know, but if you do know, we thought that that could actually improve the way that you can split them. But the key thing is really, is by forcing the eventual representation that you get to be composition in nature. Meaning that as opposed to the previous way of thinking, where each of the clusters are going to encode one particular type of preference, right? So basically you go to cluster all the way through, or second cluster all the way through, the third cluster all the way through. It's basically a direct split of the data. Instead, you're going to force the autoencoders to learn things that I can combine. So meaning that here, we are going to divide them into different, okay, we don't call it clusters, we call it facets. We call it facets because eventually in order to produce a representation, I have to be able to combine something from each one of them. So I'm going to take something from the first facet, I'm going to take something from the second one, I'm going to take something from the third one. And in that combination, I'm going to produce the eventual recommendation. Which means that there is a degree of competition among the different facets, different factors within the same facet. So in that sense, we are trying to force the representation to try to split the features by things that can be separated so that I can combine them later. So the thinking here is that I would like to be able to learn these different attributes without actually having to specify them. So we may not know, the brand or the factor and so on, but we are trying to figure out what sort of groupings are going to split the data in a certain way, but then I can combine them to eventually perform the eventual clusters that we need. Now, the advantage of doing that is that then we get these different representations that we hope are going to give us a little bit more sense of, these are the product titles that get split into different ones, right? These are for movies in this case. Now, you have the genre there, like action, adventure, drama, science fiction, and war and so on, but we didn't actually use it in the training. These are just to describe to you that eventually the things that group together, they tend to feature the same genre of movies, like certain combinations of them. So you've got like a action adventure in one sense, comedy and drama in another sense, or basically mainly dramas in this sense. Yes.
Is there any work that use contrastive learning for this task?
Yes. Yes. So you pretty much have to do that because we try to separate the yeah.
So is the performance of the contrastive learning better than the autoencoder?
So contrastive learning, these are also autoencoders. Contrastive learning is just part of the objective function when we try to train the autoencoders. In particular, we want this different, in this particular case, we want these different facets to be well separated from one another. So it means that there is a separation between different facets and there is a separation between different groups of the same facets. So you can think of it almost like these are attributes And these are the different values of that attribute. Right? Okay, so I would actually end more or less there because I kind of want to get you a sense of the thinking behind these things. And I told you earlier that to me it feels like it's coming full circle because of course now the big question of the day is how does LLM feature in all of this? And it turns out that we thought that originally the problem was primarily driven by ratings and user behavior and so on. And we realized that, hey, you need additional data to address the sparsity. And that is where things such as the text, images, and so on come in. With LLM, you actually have so much of this data to the extent that the problem now is turning back to the lack of personalization. Meaning that even if you can think of how to use LLM, at least the ways that we are seeing recently, in the way that people are thinking about using LLM recommendations, is still to some degree heavily involved by prompting. So here I think is the idea that you can fully describe a user's unique preference just by textual description. And we don't, okay, at least we don't think that is yet a perfect solution to the problem. This is essentially why we're thinking that we might have to go back to some of the original ways of modeling user behavior, and then we need to get an LLM to work with that. So meaning that if you think about some of the original modeling, like matrix factorization and so on, they are working with the raw data of user preferences. They are very uninterpretable, it's very difficult to work with them and so on, but they get to model the user space well. Whereas the current LLMs are built on the premise that what you want most of the time is some form of objective information, but we try to cheat the LLM into telling us something subjective by prompting. Which at this point of time, we don't know yet whether it's going to be a good solution. My sense is that that's probably not the solution that we want. It's likely going to have to work through some form of a combination of what we think about the ratings in the preference space and what the LLMs can do for us. I think that's still an open question, right? So I think a lot of people are working on that problem. Some of you might actually be looking into that as well. Okay, so at this point I'm going to stop the talk so that you have time to ask questions as well. Yeah.
Right. Thank you very much. Okay, so we have time for questions.
You can ask anything.
Yeah, ask anything about the research, about studying or research.
You can share your own research too. I don't mind. Yeah. Yes.
Yeah. So my first impression of
Okay.
the work is you present a lot of works that relates to variation of autoencoder.
Okay.
And yeah, it's just what I am working on.
I see. Okay.
And I built like different like world model and generative models and stuff like that.
Okay.
And I think like there's in this one of the models that you use like beta VAE in what's the model name, Macrit VAE?
Yeah.
Yeah, and I think when I tried that model, so basically the objective of the model is, for example, the tail divergence between the posterior and the prior. The prior is just Gaussian distribution of 0 as a mean and 1 as standard deviation,
Okay.
stuff like that.
Okay.
And I think it's when you increase the beta terms of the KL divergence, the KL divergence terms gets like larger and it's more unstable.
Yeah.
And even though it is boosting the disentanglement of the latent representation, but
Yeah.
I think like there has to be some other ways. For example, they do like VQ VAE something like that to more boost the disentanglements inside the latent representation more efficiently. But yeah, that's just a thought of me that beta VAE is actually not really
The best.
efficient. Yeah.
Okay. Okay.
But yeah, I think it's very interesting how you use the VAE in like the work of encoding and decoding, for example, user ratings, stuff like that, and then yeah, basically that's it.
Okay. Okay. Yeah.
Yeah.
So on the point of why is it that we feature VAE a lot, right? I think it comes down to a lot of the recommendation problem. Essentially, I think of it as almost like a clustering and representation learning problem. Because it's seldom the case that we try to predict like a unique class and so on. In fact, I think what we are really predicting is which cluster a person should belong to, because then the eventual recommendation comes from what other people in that cluster did in the past, right? So and in the branch of neural networks and deep learning, I think the class of problems that are most similar to this are basically the autoencoder space. Yeah. Now, the mechanism of it, right? Yeah. So you make a right point in the sense that there are probably more than one way to achieve disentanglement, and you can, and there is probably a cost to doing so, because in a way, it's almost the way that we build any model, is that if you try to it's just like what they say in physics, right? Like all models are wrong, but some are useful. So the thinking is that when you try to build a model of something, you're probably going to sacrifice to some extent the accuracy in the way that it reflects the real thing, but you try to make it a bit simpler so that you can understand it. And I see this entanglement essentially in that space. Maybe I'm willing to gain less accuracy if at least I know what's going on inside the model.
Yeah, it's like no
Yeah.
freelance theorems.
That's
where,
right, yes.
There's no model is better than everything.
Yes.
Yeah.
Yes. Yeah. But that's a nice comment.
Yeah, thanks.
Any other questions? So we have some freshmen here. And, I think you entering into research, right? Do you have any questions? Ask for advice? You?
Yes.
Question. So I trying to understand the problem. Yes. So after the learning the representation,
Yes.
so we have to kind of predict the. Is that like the classification problem for the recommendation?
So when we talk about representation learning problems, they are closer to what we call like feature representation problems. So some of the, for example, the most foundational things are like things like PCA. Basically, you have some data and then you try to reduce it to some smaller dimensions. And so, I mean, the basic idea really is this thinking that although a lot of data that we see are high dimensional, but they're all there to reflect something that is very low dimension. So for example, let's say today, right? I mean, if I can take a picture in the room, I probably get a very high dimensional image, but that is only a reflection of a three-dimensional reality, because the world that we live in is just 3 dimensions. So then how do we discover back the 3 dimensions from the biggest images, right? That's basically what representation learning does. Now, so in the context of recommendation problems and so on, the high dimensional space is really in terms of the actionable space of all the possible items that the user could possibly want. But we don't think that you need to go to that high. Most of the time, we think of preferences in much smaller dimensions. If you think about clothing, you think about color, you think about style, you think about certain things and so on. So then how do we discover back these lower dimensional representations of the data? So most of the time, you don't predict a class. Most of the time, you try to find a way to basically like encoding, decoding, like compress and decompress. So then the compressed form is what we call the representation.
Are we doing like clustering or unsupervised?
Yes.
What downstream class is the unsupervised one?
It is. I consider unsupervised learning. Yes, because you start out with the data itself, and then you try to reproduce back the data itself. So you're trying to find some feature space that will.
So
yeah.
how do we evaluate the representation?
How do we evaluate it?
The representation we learn from.
How do you evaluate whether it's okay? So one way to evaluate this is okay, because the representation usually is regular dimensions. You think of it as a form of compression, right? But a lot of times these compressions are lossy. Lossy meaning that they are not going to feature back the original data perfectly. So one way to look at the quality of this is by seeing how much information you lose. So that means you try to reproduce back the data and then you see how different it is from the original one. But at the same time, you can do that also with testing data, meaning that because now what you have is a compression engine, then you can test it on unseen data and then see whether they generalize well. And the third way to look into this is to look at whether or not the representation you get are actually useful. So sometimes the way we do is that you use it in some other downstream tasks. For example, you use it in a classification problem and you see whether or not it improves your accuracy.
What are you working on, Tik?
So right now I'm working on security.
Security. Okay.
But I'm trying to convert it to self-supervised learning, and I'm really interested in the asset condensation,
Okay.
Which is like instead of training the model on like 50,000 samples, you just need to train it on like 50 samples.
50?
Yeah, for each class.
Okay.
So I'm kind of interested in that direction, but how can we like synthesize the data set, but like the unlabeled data set? So
I see.
I think it's the kind of deep problem.
Okay.
Some sort of compression, right?
Yeah.
So how do you apply that to security?
So for security, there's like a type called the backdoor attack.
Okay.
And so, which is like when you train the model from third-party services, and
Yeah.
then there's a security risk that
Yeah.
the model may be poisoned.
Yeah.
And after the model is poisoned, and it's sent back to the user, so
Yeah.
how can you defend the model? So basically, what people often do is that they will fine-tune the model on the like what we call the defense set. There's a separate subset of these samples, so it will like it make advantage of the catastrophic forgetting characteristic.
Okay.
So what I'm doing now is that like that is the assumption they have. So they have the assumption that they have to have the clean data set.
I see.
So
I see.
how can we like instead of how can we like just get rid of that assumption? So I'm thinking of like somehow we synthesize the original training data set, but there's a risk that the training data set, the original training data set is poisoned.
I see. I see. Okay.
Yes.
Interesting. Yeah. Yeah. Interesting. Yeah.
Any other questions from the audience? So the last comment there is, all the work that he shared today is, the first order is Vietnamese. So one of the interesting thing is that at some point in Preferred.AI group, there are a lot of Vietnamese students, but I think it changed over time, right? Now you.
I think today is still about half of Vietnamese.
Okay. So I think he has some, I don't know, like connection to Vietnam. Yeah. So pretty much he understand us as students, and I would say I learned a lot from him as well, both from research and knowledge, but also things like the way you think and the way you educate young generations. So something I would like to share about. So. All right, so I think we're also reaching the end of the hours. So if you have no more questions, I think he's going to be around for like a couple of like 30 minutes more, I guess.
Yeah. Come by and say hello. Yeah.
Yeah, I just want to say something to him. Feel free to approach him. And thank you everyone for coming.
Thank
and
you.
Let's thank Preferred.AI once again. All right, thank you for coming.
Thank you.